So, back in 2019, there was this group of researchers who built a text prediction engine that was just so unnervingly good at generating fake news that they actually refused to release the full model to the public at first.
Yeah, they called it too dangerous.
Right, exactly. Too dangerous. But then, just 4 years later, that exact same core mechanic is sitting behind a simple chat window, boasting 100 million active users.
Yeah.
And, it's fundamentally rewiring how you, me, and literally every software engineer on the planet builds applications.
It's an insane trajectory.
It really is. So welcome to the Deep Dive. We are doing something incredibly exciting today. We're tracing this massive architectural timeline based on some really comprehensive materials we've gathered.
Right, specifically tracking the evolution of large language models from GPT-2 all the way up to GPT-4 and this whole open source rebellion.
Yeah, and our mission for you today is to map exactly how these systems transition from these isolated academic experiments into the actual commercial foundations of the modern software stack.
Because it really is the foundation now.
It is. We're going to look at an evolutionary timeline that feels like the entire history of computing compressed into just 4 dizzying years.
4 years. It really is a compression of history, and it's a fascinating one to unpack. But to set the stage for you, it's crucial to understand that this journey from 2019 to today, it's not just a hardware story.
Right. It's not just computers got faster.
Exactly. It's not just computers got faster and models got bigger. It's a fundamental shift in the paradigm of computation itself. I mean, we are moving from deterministic programming, where you write explicit if-then statements, to probabilistic reasoning.
Which is a huge leap.
It requires a total mental pivot for anyone writing code today.
Yeah, you're no longer writing the exact path. You are steering a probability engine.
Yeah.
And, well, every massive paradigm shift in tech starts with the proof of concept, right?
Always.
So for modern LLMs, that foundational proof was GPT-2 back in 2019. Now, the defining characteristic of GPT-2 was its scale at the time, which was 1.5 billion parameters.
It sounded huge back then.
Right. And its main achievement was proving that next token prediction at scale produces just startlingly coherent text generation. So, okay, let's unpack this for a second.
Yeah.
Because if you look at the underlying mechanic, it is essentially playing the world's most advanced game of guess the next word.
Autocomplete on steroids.
Exactly, it's autocomplete.
Yeah.
So how does simply predicting the next token in a sequence somehow result in paragraphs that sound exactly like a human wrote them?
I know, it sounds like magic, but it's purely mathematical. What's fascinating here is that the breakthrough wasn't some complex logic programming,
Right.
There wasn't this massive database of pre-written templates or like grammatical rules hard-coded into the system. The architecture's objective was shockingly simple. It just looks at the previous sequence of words and calculates the mathematical probability of the next word.
Just raw probability.
Just probability. But the key to unlocking the actual comprehension was that parameter count.
Okay, let's define that for the engineers listening who might be a little newer to the machine learning side of things. When we say 1.5 billion parameters, what does that actually look like under the hood?
So think of parameters as billions of tiny adjustable volume knobs, right? And they connect mathematical representations of concepts.
Okay.
During training, if the model sees the words barking and dog together frequently, the knobs connecting those concepts get turned up. If it guesses the next word wrong, the knobs adjust slightly.
So that's constantly tweaking itself.
Exactly. Now, when you apply that basic mechanic across an ocean of internet text like billions of pages, the model isn't just learning vocabulary anymore.
What is it learning then?
Well, to accurately predict the next word in a really complex sentence, it is forced to internalize the underlying structure of language. It has to learn grammar, syntax, and even basic facts about the world just to get better at predicting that next token.
Oh, wow. So it's like if you force someone to memorize enough sheet music to guess the next note in any symphony, eventually they just accidentally learn music theory.
That is a perfect analogy, yes. GPT-2 proved that core mechanic. It validated the theory that if you give a neural network enough data and enough parameters, next token prediction stops being mere autocomplete.
It starts looking like genuine structural comprehension.
Right. If it's reading a mystery novel and has to predict the final word revealing the killer, it actually needs to have tracked the clues in the preceding text to make a statistically accurate guess.
That's wild. It was a massive academic victory. But predicting text in a lab is very different from building a commercial software product.
Oh, totally different.
So we jump to 2020, and here is where the scale goes absolutely nuclear. Enter GPT-3.
the big one.
Yeah, we moved from 1.5 billion parameters
Mhm.
to a staggering 175 billion parameters.
Over 100 times bigger.
And two massive developments emerged from this leap. First, the launch of the API, and second, the demonstration of emergent few-shot learning.
Both were huge.
Let's start with the API, because for you software engineers listening, this is the infrastructure game changer. Here's where it gets really interesting. Before the API, running an LLM was like trying to generate your own electricity with a massive coal plant in your backyard.
Pretty much.
You needed millions of dollars in highly specialized GPU clusters just to load the model into memory.
The operational overhead was impossible for a normal startup. I mean, you needed a team of PhDs just to keep the servers from melting down.
Exactly. But the API was the invention of the power grid. Suddenly, you didn't need the coal plant. You just needed an API key and a basic REST call.
You plug your application into the wall, and the intelligence just flows into your software.
It changed everything.
It changed the entire trajectory of the field. By abstracting away that monumental infrastructure, OpenAI transformed AI from a pure research pursuit into a commercial platform overnight.
Right, it became a product.
They single-handedly launched an entire new startup ecosystem because anyone with an idea and a text editor could suddenly route complex natural language tasks through this massive 175 billion parameter brain.
But to understand why those startups could actually build useful features like text summarization or, sentiment analysis, we have to look at the other breakthrough you mentioned, right?
Emergent few-shot learning.
Right, because in the old days of machine learning, if you wanted a model to translate English to French, you had to explicitly train it for that task.
You did.
You had to feed it thousands of translation pairs and physically update the underlying mathematical weights, those volume knobs we talked about, through a process like backpropagation. It was highly specialized.
Precisely. You were building a custom machine for a custom task, but with GPT-3 at 175 billion parameters, something entirely new emerged.
You didn't need to update the weights anymore.
No, you didn't. You could just give the model a prompt with a few examples of what you wanted, say 3 examples of an English sentence followed by its French translation, and then you just give it a new English sentence.
And it just does it.
The model would suddenly learn how to do the task on the fly. The sheer scale unlocked this cognitive flexibility where the context window itself became a kind of temporary RAM.
That is just mind-blowing from a traditional software architecture perspective. I mean, you aren't writing new functions or deploying new back-end services for a new feature.
Not at all.
You are just passing a few examples in a plain text string, and the system executes the new behavior perfectly. The prompt literally became the new code base.
It completely blurred the line between data and instruction. But, and this is a big but, as any engineer who played with the early GPT-3 API knows, there was a massive catch.
Oh, yes. The alignment problem.
Yeah.
Because developers quickly realized a fatal flaw in this raw power grid. You plug into it, but the model fundamentally does not care about the truth, right? And it does not care about solving your user's problem.
It only cares about statistical probability.
Right. So if you sent a prompt to raw GPT-3 asking, what is the capital of France?
Yeah.
It might not answer Paris. Because statistically, on the internet, a question is often followed by another question.
So it might just output, what is the capital of Germany? What is the capital of Italy?
You thought you were writing a trivia quiz.
That is the alignment problem in a nutshell. The model was incredibly capable, but fundamentally unaligned with human intent. It was just a pure statistics engine.
Like a brilliant but easily distracted professor.
Exactly. A brilliant, literal-minded savant. You give it a command, and instead of executing the command, it just rambles on, completing the pattern based on the vast, messy data set of the internet.
So if you're a developer trying to build a reliable application, this is a total nightmare. You can't have your customer service bot randomly generating more customer complaints just because it fits the statistical pattern.
No, you definitely can't.
We needed an editor. We needed a way to mathematically force the statistics engine to actually care about utility. And that brings us to the breakthrough in 2022. Instruct GPT and a mechanism called RLHF.
Reinforcement learning from human feedback.
Right. Now, I want to get the mechanics of this right. With RLHF, did they just go back in and rewrite the model's core weights to make it nice and helpful?
Actually, no, they didn't. The base model, that raw 175 billion parameter intelligence, stayed largely the same. What RLHF did was add a behavioral filter.
A secondary layer.
Yeah, a secondary layer of training on top of the base model. And the mechanics of how they did this are really fascinating because they didn't just have humans sit there and rate every single answer the model gave.
Though it never scale. Humans are too slow for millions of parameters.
Exactly. So they used human ratings to train a second AI model.
Oh, interesting.
This second model is called a reward model. Its only job, its entire architecture, is designed to look at an answer and predict how a human would score it.
Like an automated digital judge.
Exactly. Once they had this judge, they let the original language model practice generating answers millions of times against it, using an algorithm called proximal policy optimization.
Wow.
So if the original model rambled, the digital judge gave it a low score and it mathematically adjusted its approach. If it directly and concisely answered the instruction, it got a high reward.
So it's literally reinforcement learning. It's like training a dog with digital treats, doing it millions of times a second until the model learns a completely secondary behavior, which is following instructions.
Precisely. And if we connect this to the bigger picture, RLHF is the unsung hero of the entire AI revolution.
Oh, so?
Well, alignment wasn't just some abstract ethical safety feature to keep the model from saying bad words. It was a fundamental usability breakthrough. It turned a feral pattern matcher into a compliant tool that a software engineer could reliably integrate into a workflow.
That makes so much sense.
It meant that when you sent a command via the API to extract data from a document, you could actually trust that the model would try to execute that command rather than just statistically wandering off into the digital woods.
Which perfectly sets the stage for what might be the most explosive moment in tech history. Because once you have a model that reliably follows instructions, it just needed a delivery mechanism.
Right.
We are talking about November 2022, the launch of ChatGPT. The materials highlight a staggering metric here. ChatGPT reached 100 million active users in just 2 months.
It became the fastest growing consumer product in human history.
But I'm going to push back here for a second, because the underlying model, GPT 3.5 with RLHF, it already existed for developers. And the interface, it was literally just a chatbot.
It's just a chat box.
We've had chat interfaces since AOL Instant Messenger and IRC in the 90s. Why was this specific UI the thing that broke the world?
Because it completely abstracted away the complex state management of interacting with an LLM.
What do you mean by state management?
Well, before ChatGPT, interacting with these models required navigating API playgrounds. You had to understand token limits, you had to manually tweak temperature and top settings to adjust the randomness.
Oh, right, all the technical knobs.
And most importantly, LLMs are inherently stateless. They don't remember the previous thing you said.
Right. If you ask a follow-up question via raw API call, it has no idea what you're talking about unless you manually append the entire previous conversation history to your new prompt.
Exactly. It was an environment full of friction, built by developers for developers. What ChatGPT did was brilliantly map a deterministic, familiar user action, sending a text message, to a complex, probabilistic engine.
Ah, so the UI handled the memory.
Yes, the UI handled the memory. It automatically managed the context window, appending previous turns so it felt like a continuous, stateful conversation. By wrapping this incredibly complex neural network in a familiar chat interface, OpenAI removed every single ounce of operational friction for the end user.
It is a massive lesson for anyone building software right now. I mean, you can have the most powerful back-end infrastructure in the world, you can solve the alignment gap, you can have emergent, few-shot learning.
But if the user has to jump through technical hoops to access it, it remains a niche tool.
Exactly. The chat interface democratized access to the reasoning engine.
It shifted the mental model of the general public. Overnight, AI went from being a sci-fi concept or a complex data science tool to a helpful assistant you literally just talk to.
Which naturally pushed the arms race to the next level. Because once ChatGPT won the consumer interface war and proved the massive market demand, the battle shifted back to the underlying capabilities of the models themselves.
And crucially for our engineering listeners, who gets to control that infrastructure?
Yes. This brings us to the frontier models and the open source rebellion. In 2023, we see the release of GPT-4. And the big shift here is multimodality.
It's not just text anymore.
Right? It's ingesting images, it's processing audio natively. It brings what is described as professional-level reasoning to complex tasks. And then GPT-4 comes along to make those frontier capabilities radically faster and cheaper. But they're completely closed systems.
Completely closed.
You interact with them strictly through OpenAI's proprietary API.
Right, they are black boxes. You send your data to their servers, they process it, and they send you the result. You have no visibility into the weights, the training data, or the exact internal mechanic.
And if you're writing code today, You know the frustration of relying on a closed API. You're subject to rate limits, pricing changes, and massive data privacy concerns.
Huge privacy concerns.
But then Meta enters the chat, they release LLM, and they don't just put it behind an API, they open source the model weights. They hand the actual compiled brain over to the public.
Which was a shock to everyone.
Yeah. So what does this all mean for the architecture of the web going forward? We suddenly have this massive contrast.
This raises the most important architectural question that will define the next decade of software engineering. Up until Meta released Llama, OpenAI held a near monopoly on frontier language models. Meta's decision broke that monopoly wide open.
It democratized the underlying technology itself, not just the access to it.
Exactly. It's the classic tech battle all over again.
The walled garden versus the open bazaar. It's iOS versus Android. It's Windows versus Linux. Only now it's playing out with the most powerful technology we've ever invented.
And when you look at the fallout of Llama, you immediately see this massive ecosystem of open source variants springing up. When you put a powerful model in the hands of millions of open source developers, they start tinkering.
What kind of tinkering?
Well, they find ways to quantize the models,
Quantize.
compressing them so they can run locally on an M1 Mac or even a smartphone without needing a massive server. They fine-tune them for highly specialized tasks like coding assistance or medical analysis.
It fundamentally changes the privacy landscape too, right? I mean, if you're a hospital or a law firm dealing with highly sensitive client data, you legally can't send that data over a REST call to a third-party server.
No, that's a massive compliance violation.
But with an open-source model like Llama, you can pull the model down, host it on your own secure air-gapped servers, and run the intelligence entirely locally.
Exactly. It forces a profound architectural choice for the software engineer. Do you build your application depending on a proprietary closed system like GPT-4?
Right, where you get the cutting-edge reasoning, but you're locked in.
Yeah, you get flawless multimodality and zero infrastructure headache, but you are locked into a single vendor's ecosystem. Or do you leverage the open source Llama ecosystem?
Which gives you complete control.
Control, the ability to run locally for privacy, and extreme flexibility, but it requires you to manage the deployment, the optimization, and the operational overhead yourself.
It is the literal foundation of the modern software stack that we are going to be building on for the next decade. Let's do a quick recap of the journey we just took, because it is wild to look back at the compression of this history.
It really is.
We started in 2019 with GPT-2, where 1.5 billion volume knobs proved that predicting the next word forces an engine to actually comprehend language structure. We scaled that up massively in 2020 with GPT-3, hitting 175 billion parameters.
The API era.
Right. That scale gave us the API power grid and emergent few-shot learning, where the prompts became the new code base. Then we hit the alignment problem. Raw models just generated statistical noise, so in 2022 we used RLHF training, a secondary digital judge, to mathematically force the models to follow human instructions.
You're a real game changer.
Later that same year, ChatGPT wrapped that complex stateless technology into simple, stateful chat UI, abstracting away the friction and becoming the fastest-growing product in history. And finally, we hit today's architectural battleground.
Closed, multimodal, frontier reasoning pushing the limits, while open source models spark a global rebellion of decentralized local innovation.
It's an incredible timeline, and it shows how quickly the constraints of software engineering are changing. We've moved from writing strict, deterministic rules to orchestrating complex, probabilistic reasoning engines.
If you are writing code today, understanding the mechanics of this evolution isn't just tech trivia, it is the literal roadmap of where our entire industry is headed.
Absolutely.
And it leaves us with something really profound to consider as we look to the future. Think about that moment in late 2022. The underlying RLHF technology already existed. It was sitting there, incredibly powerful, ready for developers to use.
But nobody was using it like that yet.
Right. It took wrapping it in a simple chat window to unlock 100 million users and change the world. So looking at the immense power of the models we have right now, the multimodality, the professional reasoning, the local open source variants running on laptops, what entirely new, completely undiscovered interfaces are out there right now waiting to be built.
Oh, wow.
What is the next interface that will seamlessly map human intent to these complex, probabilistic engines and unlock the next massive paradigm shift?
That is the question, isn't it? We've seen the history of computing compressed into 4 dizzying years, and we're still just scratching the surface of how to actually talk to it. Thanks for taking this journey with us. Keep building, keep exploring, and we'll catch you on the next deep dive.